Hello, I'm Gil Carlson, Director of Technical Services for ITT Fluid Handling Division. And what we shall discuss during this segment are primary, secondary pumping basics. It would be of interest in terms of developing these concepts to go back many, many years to the basic problem that led to our development of primary, secondary pumping. And this had to do with design of a very large, complex, garden-type apartment complex in which we had a long distribution main proceeding from a boiler room. In that boiler room, of course, we had boilers, pumps, and we had a pump pumping the basic piping circuit. From this circuit, we had other circuits feeding into various buildings, and each of these buildings were served by monoflow fittings serving radiation. Now, the problem that occurred was this, that the engineer designing the building circuits was different from the engineer designing the distribution system. The engineer, in terms of design of the building circuits, oversized the piping in those building circuits to the extent that it was difficult then to force the necessary flow rate through those building circuits in order to have flow diverted by the monoflow fittings into the radiation. At the same time, the person designing the distribution system undersized the piping so that we could not provide sufficient flow rate from the distribution main and into the garden-type apartment buildings to provide the necessary flow rate through the monoflow fittings to cause diversion, to cause the radiation to heat. Well, this developed into a very substantial problem. And the solution was very difficult, or we thought so at the beginning. Our first thought, of course, was to simply place extra pumps in each of these circuits so as to increase flow rate. But the building circuits were vastly different in terms of size, and it was soon determined that if we secondary pumped in this manner, that what would happen would be that one of those large pumps would simply overcome the flow head characteristics of one of the smaller pumps, and we would have a very complicated, unworkable system. It finally developed that our solution was this: to take each of the takeoffs into the secondary circuit and provide a section of pipe that we called common pipe. And with that common pipe, we were then able to disassociate the pumping of the building circuits from the pumping of the primary circuit. We then added pumps to each of the buildings, and because of the addition of the pumps, we're able to provide the necessary flow rate through that secondary circuit in order to establish the proper flow to allow the monoflow fittings to operate properly. And because of the disassociation of the secondary circuits from the primary circuits, we were able to provide a workable solution. We had, of course, to increase supply water temperature through the primary distribution system slightly. And because of this and the mix that occurred then at the inlet to the secondary building circuits, we're able to provide a completely workable system. Now, this then proceeded in terms of application from this very simple example, derived from desperation, if you will, into massive usage of primary, secondary pumping techniques. To illustrate what was done in this example, the original systems were designed for 200-degree water temperature and designed for a 20-degree delta T. So let's look then at one of these buildings in terms of application as related to primary, secondary pumping flow mix. We came from the distribution main, provided our common piping, and established with the secondary pump the necessary flow rate through that particular building. Now we needed 200 degrees supply water, 180 degree return water, and had a load on the building in the range of 400,000 BTU. This established then a flow rate need in the building of 40 GPM. Now we knew we had 200-degree water temperature leaving and established that we did have a water temperature return of 180 degrees, which would occur under this circumstance because the return water temperature from the system must match from the building circuit, must match return water temperature entering into the basic return main. And we could establish, inasmuch as we had only 1/2 the flow rate need delivered for a conventional system in the primary distribution system, which would mean we had 20 GPM delivered to that circuit, that we would then establish a 20 GPM bypass of 180-degree water, and we could establish from this then as to the water temperature need that we would have to increase to in the primary distribution system to provide the necessary mix of 180-degree water returning from that circuit and entering into the building circuit, establishing a water temperature need of 220 degrees. So the solution became relatively simple, and we were able to solve the basic initial problem. Now, it will be noted that we probably would not have solved that problem had it not been for our interest in monoflow fittings at the time, and an interest which is still maintained. But let's look then at a monoflow system, because primary secondary pumping is simply the antithesis to the design principle of monoflow system design. In monoflow system design, we provide monoflow fittings. And these monoflow fittings actually create a pressure drop in the piping between the riser takeoffs. And we can, by proper design and control of the water flow in the distribution main, establish the necessary flow rate through the radiation circuit to provide the necessary heat transfer for the system. The antithesis of this would be to eliminate the monoflow fittings and the pressure drop in the piping common to the riser circuits. And because of elimination of that pressure drop, establish that we would have no flow in the radiation circuit, or which we can now reterm as the secondary piping circuit. Because if we have no pressure drop in the common piping, we cannot have established a flow rate from the primary distribution main and into the secondary circuit. The only way, given this circumstance, that we can establish flow is to provide a pump for that secondary circuit. So if we start the pump, we will establish flow rate. And a basic principle should be stated. That is to say that for any interconnected piping system which does not contain a pump, the flow rate delivered from the primary distribution system will be a function of the pressure drop that we have in the piping common to both circuits. In this case, the primary piping circuit and the secondary circuit, inasmuch as these are connected by two T's placed relatively closely together. In this circumstance, we can have no flow in the secondary circuit. And because we can have no flow when the pump is off, but we place a pump in that circuit and start the pump, we can then establish the necessary flow rate. This then is the basic principle behind primary-secondary pumping, that we disassociate the pumping of the secondary circuit from the pumping of the primary circuit by means of a section of piping common to both the secondary circuit and the primary circuit. But that piping then has very low head loss. So let's look then at some of the primary mains that are used for primary-secondary pumping. And this illustrates, the top illustration shows a one-pipe distribution main. Now we can connect to that distribution main with primary-secondary takeoffs. But so long as the pressure drop in the common piping is relatively low, the primary pump need only concern itself with pumping of the primary distribution main itself. Pumping of the secondary circuits is, in this circumstance, taken care of by separate secondary pumps. The same thing applies to a two-pipe direct return piping system, in which we have crossover bridges. And the crossover bridges, in terms of flow rate, are correlated with the secondary circuits connected to those crossover bridges. But it will be noted, again, that because we have very little pressure drop in the common piping, the primary pump is concerned only with distribution of the necessary flow rate through each of the crossover bridges. The same thing applies to a reversed return circuit, in which the primary pump, being disassociated from pumping of the secondary circuit, is only concerned with the development of the necessary flow through each of the crossover bridges. So let's then proceed from this into a discussion of the various types of controls that we can apply to those crossover bridges. Initially, One of the thoughts developed in terms of primary secondary pumping was to provide a necessary flow rate through the crossover bridge and then simply connect a single pump to radiation and or some sort of heat transfer unit in that secondary circuit so that we could provide, by starting and stopping of the pump, in this case generally a very small booster pump, the same type of control associated with residential control as used for many years. And we did apply this very satisfactorily with a constant flow in the distribution main and with the necessary flow rate provided to the inlet to the secondary pump. Now let's illustrate what has to be done for this circumstance. For this circumstance, we will need flow control valves or check valves at the discharge of the small booster pump. This pump, remember, again being used in a residential sense in which a thermostat simply stops and starts the pump. We will need check valves because despite the fact that we place the connections or common piping connections close together, we will still have some slight measure of pressure drop. The flow control valves illustrate about the order of 3/10 of a foot stat head so as to prevent any slight pressure drop in the common piping from causing flow in the secondary circuit when the pump is off. When the pump starts, it drives flow through the terminal circuits involved in this basic residential application of primary secondary pumping so that we establish then control in the same manner that a residential system exhibits control. Now you may wonder as to why it is we illustrate a second flow control valve on the return side of this system. And this is shown for this reason, that if in a system such as this we provide a relatively high flow rate of high temperature water, say to the order of 220 degrees, passing through the system, and have the return leg connected to the crossover bridge, we can, because water flows by gravity in a system such as this, establish a one-pipe flow of hot water. So hot water will go up into the piping, get cooled down by adjacent radiation, and return to the secondary crossover bridge, even though the pump is not on. And this can cause problems in terms of control. So we do then apply a second flow control valve in the return line of a system using a single stop-start pump for application. And that second control valve, flow control valve, is as shown in the initial diagram in the circled area in order to prevent a back gravity flow into closely connected radiation to that particular point. Now this would then conclude our initial start for primary secondary pumping. That is to say, the basic trouble problem that led to the development of primary secondary pumping and the initial application thought areas as to primary, secondary pumping applications.